In this submodule, we'll introduce elementary number theory. Number theory is the mathematical subject concerned with properties of integers, though the study of integers necessarily leads to study of irrational numbers, rational numbers, and the notion of algebraic numbers that I introduced in the last submodule. It's one of the most ancient mathematical subjects. The Greeks studied it, the ancient Chinese studied it independently of each other. Only in modern times have sort of the separate strands of this subject come together. It's quite pervasive. It's a core mathematical subject. It's also quite difficult. It's well known for having many open problems, rather unsolved problems still today. And in fact, it's also known for having problems that are easy to state, but very, very hard to prove. So mathematicians who work in number theory tend to get a lot of cred from other mathematicians. One notion that we need is the notion of divisibility, which you're probably already familiar with, though maybe under a different name. We say that an integer p divides an integer q if I can write q as p times r for some integer r. So for example, if I take the number 8, I can write this as 2 times 4. So 2 divides 8. Another example could be 30 equals 5 times 6. So 5 divides 30. We give a name to all the numbers that divide a particular integer. We call them the divisors, or sometimes factors, of the integer. One important class of numbers are defined through their divisibility properties. Keep in mind that any integer is always divisible by 1 and itself. This is a rather simple exercise. Most numbers seem to have other divisors, though some, of course, do not. We can think of some of those off the top of our heads. 3, for example, 5, also 2, if you write it down. The only divisors are 1 and 2. The numbers that have only these divisors, 1 and themselves, are called prime numbers. Prime numbers are very well studied, but they're still quite mysterious. There are many open conjectures about properties of prime numbers that have stood for hundreds of years, with no one able to give a complete solution. So although they have a simple definition, there are many very complicated ideas corresponding to them. So in that sense, they're really indicative of number theory. Simple to state, hard to prove. So let's look at just a couple examples to get us in understanding this notion of divisibility. I'm going to give pairs of integers, and I want to find the greatest common divisor for each of them. So the divisor that between them is the largest. So let's start with 20 and 42. So for 20, its divisors are 1, 2, 4, 5, 10, and 20. And for 42, the divisors are 1, 2, 3, 6, 7, 14, 21, and 42, so that the greatest common divisor is 2. In our next example, we have 9 and 72. So first, let's write out the divisors for 9. 1, 3, and 9. For 72, it's quite a long list, but we'll start. 4, 8, and then 9 is the divisor of 72. So now we stop to make a pause. If 9 divides 72, then the greatest common divisor between 9 and 72 must be 9, since of course 9 is the divisor of 9. So we can stop our list here and say that the greatest common divisor in this case is 9. Now we'll look at 30 and 36. So we'll list the divisors of 30. 1 divides every number. 2, 3, 5, 6, 10, 15, and 30. And for 36, we have 1, 2, 3, 4, 6, 9, 12, 18, and 36. So we look for the number among these which is greatest, and we see 6 is common to both and is maximal. So greatest common denominator is 6. For our last example, we have 8, which has as divisors 1, of course, 2, 4, and of course itself. And for 24, 1, of course, 2, 3, 4, and 8. So again, we can stop here. 8 is a divisor of 24, so the greatest common divisor of 8 and 24 must be 8. Related to the notion of divisibility are even and odd numbers. These can be understood as integers with special divisibility properties. We call the numbers which are divisible by 2 even numbers, and everything else odd numbers. We can list these out. The even numbers include negative numbers, -4, -2, 0, 2, 4, and so on, and the remaining integers are the odd ones, -3, -1, 1, 3, and so on. The reason we include these in the topic of divisibility, even though you're, I'm sure, already familiar with even and odd numbers, is because we can define them in terms of divisibility by 2. Okay? So to get a little bit of a flavor for even and odd numbers, and also to give us a taste of what some intro to mathematical proofs might be like, we're going to show that the sum of any two odd integers is even, which, of course, if you start to think of odd integers, 1 and 3, I add them and get 4. 9 and 5, I add them to get 14. It seems like I'm always adding them and getting something even. So we can actually prove this using the definition of even and odd integers. Right? So let A and B be any odd integers. Then we may write A equals 2 times some integer m1 plus 1, and B equals 2 times m2 plus 1 for integers m1 and m2. This is because 2 does not divide these integers a and b, because they are odd. What happens when I add them together? I get 2m1 plus 2m2 plus 1 plus 1, which I can write as 2 times m1 plus m2 plus 2, aka 2 times m1 plus m2 plus 1. In other words, a plus b is even, since I've shown that it's divisible by 2. So this is very indicative of the type of theoretical argument you might have for the CLEP. They might ask you to say which of the following statements about even and odd numbers is true, which are false. If you can work with the mathematical techniques from their definitions, you'll be able to understand these questions more clearly. Let's look at one more that's of a similar spirit. So we say take any two odd integers and multiply them together. I claim that that's always going to be odd. And we'll proceed in basically the same way. We'll let A be equal to 2m1 plus 1, and B be equal to 2m2 plus 1 for m1, m2 integers. So we take any two odd numbers, write them in a way I know is possible. And then I say A times B is equal to 2m1 plus 1 times 2m2 plus 1. And I distribute this and get 4m1 times m2 plus 2m1 plus 2m2 plus 1. Right? So this is good practice for our foiling. And we ultimately write this as 2 times 2m1 times m2 plus m1 plus m2 all plus 1. So we see that a times b is not divisible by 2. We get a remainder of 1. Right, this plus 1 at the end tells us that when I try to divide by 2, I'll be stuck with this remainder of 1. So therefore, I cannot be even, which implies that a times b is odd. The similar rules apply for the sums of even numbers and the products of even numbers. And these are good to think a little bit about before you take the CLEP exam. The last topic from number theory we want to look at is certainly the heaviest of them, but it is something that's covered on the exam. We call it the unique prime factorization theorem, and it goes back at least until the early 19th century, 1800s. Gauss made contributions to this and proved a famous formulation of it. The way that we will write it for this course is as follows. Every integer may be written uniquely as a product of primes. This complicated notation here just says that I take some prime numbers, potentially raise them to powers, and I can write any integer uniquely in this way. So this is product of prime numbers. So I can take any integer and decompose it into basic atoms. And these atoms are prime numbers. And I combine these atoms into my integer by multiplying. So we'll look at some examples where I'll present you an integer and ask you to factor it in terms of prime numbers. So here are some examples. Let's start with 8. So I want to write 8 as a product of prime numbers. How can we do this? Well, let's start by factoring out one prime number. I can write this as 2 times 4, where 2 is prime. So I pulled out one piece of the prime factorization. I pulled out 2. Can I pull anything else out? Well, I can decompose 4 as 2 times 2. Hence, I get a factorization of 2 times 2 times 2. Each element of this factorization is itself prime. Therefore, I found my prime factorization. If you like, you can write this as 2 cubed. Going back to the statement of our theorem before, 2 would be like P1, and 3 would be like M1. Let's look at 17 now. We'll try and write this as a prime factorization. Well, it's not divisible by 2, or by 3, or by 5, or by 7. In fact, 17 is itself a prime number. So the prime factorization is just 17, because 17 is prime itself. So a bit of a trick question. 100, well, we'll start by trying to factor it any way we can. Can we pull any prime numbers out of it? Well, sure, it's even, so I can pull 2 out. So I can write it as 2 times 50. Can I pull any primes out of 50? Sure, 50 is even. So I can write it as 2 times 2 times 25. Now I have to factor some primes out of 25. Well, I can write that as 25 is divisible by 5 times 5. So now I have a factorization of 2 times 2 times 5 times 5. All primes, so that's the prime factorization. How about 15? Can I factor anything out? Well, I can do 3 times 5. And in fact, that gives me the prime factorization. 25 we just did implicitly. This is 5 times 5, or 5 squared. We could also have written 100's factorization as 2 squared times 5 squared. Lastly, 2 is itself prime, so it's its own prime factorization. So these number theory topics won't be tested too in depth on the CLEP. They're kind of a niche market on this exam. But it is good to know about divisibility, properties of even and odd numbers, and to at least have some idea of what a prime factorization is. In particular, being able to compute one.